Thanks for all sticking around now for the next chapter. This is a very intense afternoon program. This is coming in waves. Bang, bang, bang. So now we're going to do MCD spectroscopy. And here's what I'm going to tell you about. So we're going to do a little overview over the theory of MCD. Of course, it's a little bit dry, but I'll try to keep it as interesting as I can. And then we have a case study here. Of course, my group works a lot on iron nitrosyl complexes, so I have a little bit about this here where we use MCD. And we can see how much of this we can get done in the time that I have. So here's a slide that I always show, right? Low temperature MCD, the sleeping giant. So I think it is still a very underutilized technique in bioinorganic chemistry. And I've been coming here for a couple times, as Carsten was mentioning, but I think this is still valid. There's a lot you can do, and you can learn about your system using MCD spectroscopy. So let's go back in time. In 1845, when Michael Faraday discovered what we call the magneto-optical effect. And essentially what he did is he used linear polarized light. Let's say the light is polarized like this. And then you let that light travel through a medium and you apply a longitudinal magnetic field. And then what you observe is that the plane of your polarized light is rotated when the light comes back out after passing through the medium and the magnetic field. So this is the magneto-optical effect. So the way you can think about this is, or you can explain this is, if you consider the linear polarized light actually as a superposition of left and right circular polarized light. So here's an example for circular polarized light. So you can see in this example the electric field vector rotates as the light propagates. And if you stand there in front and the wave approaches you, if it rotates counterclockwise, then it's left circular polarized light. And if it rotates clockwise, it's right circular polarized light. So this is the convention that we use here. So this would be one left circular polarized light wave, traveling up from here down to here. And now if we go and we superimpose two of them, right? So one is left circular polarized. This is the electric field vector. It rotates this way. The right one rotates that way. And then you add up the electric fields, you get this, right? And so now as you rotate this down, you can see that when we are at 180 degrees, the two will just compensate for each other. So the resulting electric field vector is 0. And then as they travel down, and then the vector points in the other direction. So if you just look at this, it looks like it oscillates in that plane, right? The electric field goes up and then to 0 and then down and up and down. And that's what it looks like. But if we consider the linear polarized light as the superposition, we can now explain what happens in Michael Faraday's experiment. Right? So when the light now travels through that medium in the presence of the magnetic field, the left and right circular polarized light waves, they propagate at different speeds. Right? And so when that happens, then essentially that causes a phase shift of the left and right circular polarized beams. And when you have a phase shift between them, that means that it looks like that the direction, the plane of polarization is rotated when the light comes out of the medium. And that would be a way we can explain this effect. Okay, so this of course assumes that the light is not absorbed by the medium, but that can of course happen, and that gets us one step closer to MCD spectroscopy because we want to absorb the light. Now what happens in this scenario now if we assume that there is absorption, but that the left and right circular polarized light are absorbed to a different extent? So if we look back at and I show the graphic in a second, then of our graphic, then what happens is we go from linear polarized light to elliptically polarized light. So if we draw this up now, you can look at this like this. So we have again the left and the right circular polarized light beam, but now because in this case we absorb the right circular polarized light stronger than the left circular polarized light, you can see these electric field vectors now have a different length here. So again, we can superimpose them, but then when we go to 180 degrees, they do not exactly compensate anymore. So there is residual electric field here, and then if we follow this around, we get an ellipsoid. So we go from linear polarized light to elliptically polarized light if the medium actually absorbs our light waves. But the important thing is that the left and the right circular polarized wave are absorbed to a different extent. Right? So we could measure this. We can, again, start with the linear polarized light and then measure this ellipticity that results from this in the Faraday experiment. So if we kind of summarize this up, then we have essentially two effects, right? So we have, for one thing, is the rotation of the direction of the plane of linear polarized light as one effect here, magneto-optical effect. It's the real part of this effect, and then the imaginary part leads to the absorption of the light, and that causes the light to go from linear to elliptically polarized light. So now you might ask yourself, okay, that's all nice and easy, but how the heck is that going to help me now when I'm studying protein XYZ, and how can I learn something about it, right? So there is actually something that this is actually useful for, but we have to do this not by looking at the linear polarized light, but we have to look at this more through CD spectroscopy. So we measure the absorption of the left and the right circular polarized light and get a spectrum and then go from there, right? So if you look at CD spectroscopy now, we measure, again, as I said, the difference in absorption now of left and right circular polarized light. So we have a delta A of absorbance, and we can treat this with a Lambert-Beer law, as this is shown here. So if we know the path length and the concentration, then we can transform this into a delta epsilon now. So an extinction coefficient that will be then defined through the difference in absorption of the left and right circular polarized light. So this will be the starting point. This is, of course, your CD experiment, and then in MCD, you want to now use the magneto-optical effect, so we're going to add a longitudinal magnetic field onto this, right, and then measure the CD spectrum in the applied magnetic field, and then also, as we will see, we'll usually do this at low temperatures. We have to go down all the way down to liquid helium temperatures, as we will see, in order to do this. So it is a bit of an expensive experiment to run. And here's one of the kind of the godfathers of the field, P.J. Stevens. He is really the one who took this from Faraday's equations then really to formulate the basic equations for MCD spectroscopy. So there's a big jump now. We're not going to go through all of this, but we can see what the result is, and that gets us to the fundamental equation of MCD. We can understand then what the different types of intensity mechanisms are. So he worked on this and published some really important papers back in the 70s on this. Here's an experimental setup. This is the one in my laboratory, but it's pretty typical, right? So you essentially have two pieces of equipment you have to buy. So you need the CD spectrometer in order to get your CD spectrum, in order to get your circular polarized light and measure the absorption of this, or the difference in absorption, and then you need to be able to put your sample into a magnet. So here's our cryomagnet, typical Oxford magnet, where we have the sample here down. You can't see this now in an optical tailpiece, and we cool this with liquid helium, and there is a superconducting magnet in there that can go up typical fields of 7 or 8 Tesla. So there's an additional cost then arises from the fact that you have to cool that magnet, of course, to run the experiment. And then the detector sits here somewhere at the end of this box. The problem with this is that the magnet has a pretty strong stray field, and so you're trying to just separate the spectrometer on the one side, the detector on the other side, a little bit here from the cryomagnet that's in the middle. That's why you have this kind of long setup here. Otherwise, there is really no reason to do this, right? But it's a practical reason. And then also we kind of built this coffin here around it, so you could now run your experiment, because you have the beam just traveling as an open beam through this box here, but you can have the light on while you run the experiment. So this whole setup is really just dictated by kind of these practicalities. Okay, so here it is now. Here is the magic. This is the basic equation of MCD spectroscopy, or fundamental equation that was formulated by Stevens back in the 1970s. So if you look at this equation, you see that there are 3 contributions to MCD spectroscopy. So here, this will be the intensity that we measure. It's proportional to this A, B, and C term. And you notice there are some interesting differences here. So for example, if this is the F of E, this is an absorption band shape. So in the easiest case, you could think about it as a Gaussian band shape, right? So F of E is your absorption band shape. You can see that the B and the C term have absorption band shapes, but the A term does not. So in the A term case, we have the derivative, first derivative, respect to the energy of your radiation, your light, and so then you get a signal like this. So there are 2 different types of signals that you can get here. You can also see there is a temperature dependency for this so-called C term. It's 1 over T. And then beta is the Bohr magneton, so sorry, back to beta. And here B is essentially our magnetic field. So also the intensity is linear with magnetic field, is what this theory predicts. So if you double your magnetic field, you double your intensity. That's not entirely true, as we will see a little bit later, but it's a good starting point. Okay, so then you always hear people talking about, I measured an MCD C-term signal, or I have an A-term signal here, and so that really relates back to the way how Stevens named this, right? He could also name this apple, oranges, and bananas. And you would say, I have a banana MCD signal. So no, instead we have a C term. All right, so if you look at just the intensity relation to the C term, you notice the Curie law that's in there, right? So there's something to do with magnetization in the ground state. Here's the Curie law, the magnetic susceptibility, constant over T, and you can see there is the same kind of formulation in here. So we'll see later why that is. But here's a plot just of the Curie law that kind of shows this 1 over T dependence, either the magnetic susceptibility, so this is this curve here, or then here 1 over, then it gives us a straight line with the slope 1 over C. Okay, so, before we go there, not forget the MCD selection rule. So if we take a simple example, we take like a copper 2 complex, S equals 1/2. Now we put this in a magnetic field. The Z-man effect then will come in and it will split our here ground state, and A is the ground state, J the excited state. Split this into the magnetic sublevel. So here is only plus minus 1/2. Right? Then we have transitions where now the change in the magnetic quantum number could be either +1 or -1. And that relates here to the MCD selection rule. So the left circular polarized light follows a change in the magnetic quantum number of +1. So in this case, from the -1/2 to the +1/2 component. And then for the right circular polarized light, the change in the magnetic quantum number is -1. So this is the MCD selection rule. Okay, so let's look at these different mechanisms and where they come from. So the first one is the so-called A term. And the A term requires that we have a degenerate excited state. And this is the equation for the A term. It's a little bit simplified equation. So here we assume that the magnetic field is along the Z direction. So by doing this, we can make this equation a little bit easier. And then you can see we have 2 parts in the equation. So here's the Z-man part, right? So this is the Z-man splitting of the excited state. This is the Z-man splitting of the ground state, with this being the Z-man operator here, typical. And then we have these electric dipole parts. So you can see we have 2 electric dipole matrix elements squared, and one is for the absorption of the left circular polarized light, the other one for the absorption of the right circular polarized light, and we'll take the difference here. So you can see then these electric dipole operators, mu minus and mu plus, are defined like this. So they have an x and a y component. Right? So remember that we have circular polarized light, so the electric field vector is rotating around. So in this case, then, if the magnetic field is in the Z direction, we can induce transition in the XY plane, right? And we have to have transition dipole moments both in X and Y direction. So we have to have this kind of degeneracy in this way, because we need absorption both in X and Y direction, since we're rotating the electric field vector around. So if the magnetic field is in Z direction, we can only get transitions in XY. But then, of course, we can have all different orientations, of course, in our sample. This is just projecting out along the Z direction. So let's see. Okay, so here's a practical example of what that looks like. So you can have an A term for a diamagnetic compound. So it's here a simple ground state. Let's say we have a degenerate excited state, orbitally degenerate excited state. The MS0 component are left out. So here the plus minus 1. We apply, and this is without the magnetic field. We get 2 transitions, but they have exactly the same energy. And since this is a degenerate excited state, they have exactly the same intensity. So they cancel each other out exactly. And the resulting spectrum here is that green line. Nothing happens. But now when we apply the magnetic field, you can see there's a slight difference in the transition energy due to the Z-man effect and the Z-man splitting here in the excited state. So now we're taking our 2 absorptions, the red and the blue one, and we're offsetting them just a little bit. And then when you take the difference, then you can see this kind of derivative-shaped signal results from that. Right? And that is the A-term signal. So you can get actually an A-term signal for a diamagnetic compound if you have, for example, orbital degeneracy in excited states. And for porphyrins, for example, right, they have these E types of excited states. You can measure these A-term signals. 1 second. Okay, so next guy here is the B-term mechanism. In the B-term mechanism, it looks a bit more complicated, but essentially what we have now is that we have a non-degenerate excited state, and then we have a second auxiliary state, which is called K here, very close in energy to that excited state, and then these 2 states, they will mix under the Z-man perturbation. And you can have both scenarios. So you can either have the excited state J interact with this auxiliary state. You could also have the ground state A interact with the auxiliary state. So both of those are allowed possibilities, but the important thing is that they mix under the magnetic field, under the Zeeman perturbation. So if the magnetic field is turned off, there is no mixing and there's no signal. And then as you turn on the magnetic field, this mixing increases as the strength of the magnetic field increases. So this is this part here, and then again you have, of course, the electric dipole part describing your transitions, your absorption of the left and right circular polarized light. You can see now we have these mixed products though. So we have here, for example, the transition from A to J, but then also a transition between the ground state and this auxiliary state comes in here, the equation. So two possibilities. Again, we can look at this with a little diagram here. So now we have, so we're interested in the transition from A to J, let's say, and then we have an auxiliary state K here. Now, if the magnetic field is turned off, there is no mixing, so there's no transition. If the magnetic field is turned on, then we will get our two transitions. The important thing here now is, though, that the transition dipole matrix elements for the red and the blue transition are no longer the same. In the A term, it's a degenerate state. So the electric dipole matrix element or transition probability is the same for both of them, but now these are different states, right? They have different extinction coefficients, if you want to say it like this, and that means they do no longer cancel. Let's say one is bigger, one is smaller, and if you take the difference, now you end up with an absorption band shape, no longer a derivative band shape for this B term, again, generally speaking. So, yeah, this is what this is, and again, as we've seen before, so both the A term and the B term are linear with magnetic fields. So if you double the magnetic field, you double the intensity, and that is strictly speaking true. The C term is the one where this is not necessarily the case. We will see in a second. So the most interesting term for us is the C term, and the C term requires a non-degenerate ground state. And of course, the non-degeneracy is really usually spin degeneracy, because if you have orbital degeneracy in the ground state, then the Antello effect is very happy to lift that degeneracy for you. So for example, in this case, we have a low spin ion free, right? You're strictly octahedral, so you would have this degenerate ground state. However, the Antello effect then will induce a distortion of the molecule. It will essentially localize that one electron in an orbital for you. And in that way, you lift the orbital degeneracy. So if we talk about a non-degenerate ground state, really what we're talking about most of the time is spin degeneracy. You have to kind of force your system in a way that suppress the Antello effect in order to get orbital degeneracy. So that means that the C term is generally only observed for paramagnetic complexes. So if you have spin degeneracy, you have unpaired electrons, you have something that's paramagnetic. Right, so the C term is a mechanism we can use to specifically look at paramagnetic centers. Here's the equation. It looks otherwise relatively similar to the A term. We have again a Zeeman part here. Now, of course, this is the Zeeman effect in the ground state. So splitting the ground state into the magnetic sublevels. And then we have our electric dipole part again describing the absorption or the difference in absorption of the left and right circular polarized light. So here's an example for this, the C term mechanism, again looking at an S equals 1/2 system. This would be done, let's say, at a small magnetic field or at high temperature. In this case, then you have essentially equal Boltzmann population of the MS minus 1/2 and the MS plus 1/2 sublevel of the ground state. And that means what you would actually get is something that looks more like an A term signal, right? Because you have essentially the same transition probabilities for both of them. You have same population. And you go to the same excited states, the same extinction coefficient. So gives you the same size band here, and the only difference then that results is there's a little shift in energy from the Zeeman effect. It's very small, so that would give you a very, very small kind of an A-term-like signal. But that's not really the interesting part. The interesting part now is we go to larger magnetic fields and lower temperature, and now what we get is a difference in population of the magnetic sublevels of the ground state, right? And although we have overall the same electric dipole matrix elements, the same extinction coefficient for the transition, we have more molecules now in the lower level compared to the higher level just by Boltzmann population. If we split them large enough, we go to a low enough temperature, we will get a difference in population. So we have a different transition probability from these two states due to the different Boltzmann population. That means we get a bigger band for the red transition and a smaller one for the blue transition. There's simply more molecules in the ms minus 1/2 state compared to the ms plus 1/2 state. The bands do not cancel out anymore, and we end up with a large signal here corresponding to an absorption band shape. Now, in the Stevens equations, it says that the C term is also linear with magnetic field, but if you look at this, you realize that can't really be true, right? Because once that blue signal here is gone, there is no way you can get more intensity. There has to be kind of a limit in intensity that you can get. So when you have completely depopulated this upper level here, this plus 1/2 level, all the molecules are down here, then the blue band is gone, and then your green essentially spectrum corresponds to the red spectrum, and you can't get more than that. So there has to be an extension to that initial equation that Stevens gave us that actually describes the saturation behavior. You can also now see the relation here to magnetism, right? Because what we're probing now is the amount of splitting of the magnetic sublevels of the ground state. We're probing their Boltzmann population, right? And that, of course, is directly also related to magnetism. So what we can do actually with MCD is we can optically now detect magnetic saturation curves. If we take a signal like this and now we measure the intensity as a function of temperature and field, we'll end up with something that looks like a magnetization curve. So that is where a lot of the additional information is in that we can extract from MCD. So we'll talk about this a bit more as we go forward. So here's just some reviews back from the old days when I was postdoc in the Solomon lab, where we kind of talk about this stuff. Okay, so we already talked about this, and I've already told you about the saturation behavior. So that's something we have to add to the Stevens equation. So we need a bit more sophisticated model to describe all of this. And generally speaking, if we're down at low temperature, the C terms are about 2 to 3 orders of magnitude more intense than A and B terms. Right? And so really the C terms are the signals that we can really measure well, that we can observe well, and that we can analyze. And then again, if we look at the saturation behavior, we can learn something about the magnetic properties of the ground state. So these are by far the most useful signals to study, and that's why usually all the MCD work focuses on C terms. Okay, and now we have another problem that when we look at not hemes, but kind of generally like a non-heme ion site or something like this, usually we don't have degeneracy in our excited states. We can have it, but generally speaking, most of the time we don't. But of course, for our MCD transition or CD transition, we need to have transition transition probability in 2 directions, x and y, because again, we're looking at this rotating electric field vector, right? But if we have a non-degenerate ground state, a non-degenerate excited state, we have a transition in one direction, right? During this electric dipole transition, electric charge is shifted in one direction in space. That gives us the direction of our polarization, and that's it. So we're one-dimensional. But in order to get MCD intensity, we need another direction. So how can we get this other direction? And the answer to this is spin-orbit coupling. We already heard this before. Spin-orbit coupling always makes a mess out of everything, and that is the same here too. So what spin-orbit coupling will allow us to do now is take one type of excited state that's polarized, let's say, in x direction, mix in another excited state that's polarized in y direction, and now we have our 2 directions that we need, and we can get MCD or C-term intensity. Right? So spin-orbit coupling comes in here as a big player for many systems, so we don't have orbital degeneracy. Now that also means that in a way our intensity scales with the amount of spin-orbit coupling that we have, and so that means if you have, for example, a metal-based transition like a DD transition, that will usually be intense in MCD because the metals have much larger spin-orbit coupling constants than something like carbon or nitrogen or hydrogen, what our ligands are oftentimes made of, right? And so if the intensity scales with spin-orbit coupling, roughly speaking, then these DD transitions, which are weak in absorption, will be strong in MCD. And then charge transfer transition, especially if you have covalent bonding between the metal and the ligand, you have a lot of metal character in the transition. You will have an intense band in MCD, but then these pi to pi star transitions that oftentimes dominate absorption spectra will be very weak in MCD. So oftentimes also we're looking at MCD and optical spectroscopy as complements, right? And we're comparing intensities. If we do this, we can maybe make some claims of whether a transition is an inner ligand transition, or if it's a charge transfer, or if it's a DD transition, where we're comparing intensities between the optical spectrum and absorption spectrum and the MCD spectrum. So this is another part here where MCD can be useful for. So here's one example for this. This is a copper complex, a copper-2 complex. Here's nitride bound to it that we studied a while ago. And then if we compare the spectra, right, this is the absorption spectrum of this complex. Note that there's a difference in scale here. So these are our DD transitions, extinction coefficients below 200. So they are tiny, tiny, and in solution, hard to measure. And then here you can see there are some more intense transitions here. This is the MCD spectrum. You can see the DD transitions now. Some of them are really big, emphasizing this point here, some charge transfer transitions, and then as we go further up, there are inner ligand transitions here, and our MCD intensity kind of comes down. Those transitions have very little MCD intensity. So that's one good thing that MCD can do, and then of course MCD is assigned intensity, so intensity can be positive or negative, and so if you have a bunch of bands that are overlapping in an absorption spectrum, they just all add up to a giant blob. But if you're lucky in MCD, and some of them have different signs, you can resolve transitions better. So here's an example. This is a copper-2 complex with a de novo designed protein that was made in the Pecoraro group that we measured. Here's the absorption spectrum. It's pretty broad. You can see there are some components here. But if you look at the MCD spectrum, you can resolve all of this very beautifully in the different transitions that are kind of hidden under this envelope here. And you noticed immediately there are too many transitions here, so that means there has to be more than one species in there giving rise to DD transitions. Since it's copper-2, it can only have 4 DD transitions, so the sample has to be inhomogeneous. There have to be 2 different species in there. Okay, so let's go up to the next step, and that gets us back to Solomon Lab, and this is that work is done especially by Frank Neser when he was a postdoc there. Now taking the Stevens equations for the C term and really adding in that part that allows us to describe the saturation behavior, right, that we observe in our curves. So this is the equation here that he derived. It's published in this paper for the S equals 1/2 system. Here's our C term intensity. So this is very interesting, and if you look at this closer, you can see we have these interesting triple products here. So the M's are transition dipole moments for transition, either from the ground state A to our target excited state J, or there is some auxiliary state K in there too. I'll show a little diagram in a second that will emphasize this. So they're transition dipole matrix elements, and they are polarized in certain directions. You see U and V. And then this L here, this is a reduced spin-orbit coupling matrix element. And there is spin-orbit coupling here between these states K and J. So at the end, we have this triple product here, or triple orthogonality, essentially, right? So we have 2 transition dipole matrix elements, 2 transition dipole moments. They have to be orthogonal to each other in this cross product here. Multiplied the vector product here with the spin-orbit coupling matrix element in the third direction in space. So we have to have 2 transitions. We have to be able to couple then these 2 excited states, or these 2 states, by spin-orbit coupling in the third direction in space, and only then will MCD intensity arise. So we call this the triple orthogonality principle, and you can see this here in these 2 contributions. Let's see. So here's a picture of this, right? 2 orthogonal transition dipole matrix elements, and then the spin-orbit coupling in the third direction in space. It's a very strict selection rule, which then really only allows certain transitions to be seen where all of those requirements are fulfilled. And then you need to have significant spin-orbit coupling in order to get significant intensity for these transitions in MCD. So let's look at these 2 different mechanisms here. For MCD intensity that are part of this equation, right? So the first mechanism is, again, we're looking at the ground state is A, and then our target excited state is J. So this is the transition we want to measure. But we need a third state, K, and we need to have those 2 spin-orbit coupled into each other. This is what this matrix element describes. And then the transition dipole matrix elements, or the directions here, the polarizations have to be different. So let's say our transition is X polarized, then the transition from the ground state to the auxiliary states, let's say, has to be Y polarized, and then those 2 states have to couple by spin-orbit coupling in Z direction. And only when all of this is fulfilled will MCD intensity arise, otherwise it won't. So that's, again, it's a very strict selection rule. This is, again, the part of the equation that describes this piece, and this is the one mechanism here that corresponds to this first part. So our auxiliary state can spin-orbit couple with our target excited state, and that will give us MCD intensity. Or, as you can probably foresee, the other possibility is that the spin-orbit coupling here is between the ground state and our auxiliary state, and then here's our target excited state. This is a particular interesting scenario here, right? Because we're coupling here essentially to a virtual transition. Since this state K is too high to be Boltzmann populated, we can't actually measure this transition from K to J. It's a virtual transition, yet we need the polarization of this to be orthogonal to this in order for this transition here, in order for us to be able to measure this transition. So kind of an interesting effect. And then again, we need the spin-orbit coupling in the third direction in space, and then we get MCD intensity. So those are the two possible scenarios how MCD intensity can arise now in this scenario. Here's an example then. This is some data that I took. It's at 2 Kelvin, and you can see here these are different magnetic fields. 1 Tesla, 2 Tesla. You can see here initially it looks like it's linear, and then it kind of seems to level off. And now we can take these intensities, we can translate this into a magnetization plot. So we plot this like a Brion curve over beta H over 2 KT. And then you can see here the intensity, and then the intensity saturating for this transition. So if we kind of look at this a little bit closer, then you can see there is a linear region here in this magnetization curve, and this is where the Stevens equation is valid. Right? So if you double your magnetic field, you double your intensity, but then as you keep depopulating the upper magnetic sublevels of the ground state, you start to go into the saturation limit, and this behavior is described ideally by a Brion curve. So just like magnetization curves in a similar way. Right? And yeah, what you measure is, of course, again, the splitting of the magnetic sublevels, the boson population over them. It's a similar thing. So here's a picture then of the Brion curves. Of course, when you measure magnetic susceptibility, right, you can look at the magnetic susceptibility here, and then here are the Brion curves for different spin states. If you essentially know the height of the curve, in a way, if you want to call it like this, that will tell you then what the total spin in your sample is. Of course, things are a little bit more sophisticated, but just kind of broadly speaking. In MCD, we can't do this because our MCD intensity, of course, also depends on the electric dipole or transition dipole matrix elements. So the absolute intensities cannot be used to determine spin state. But in some cases, when we're lucky, what we can do is we can use the shape of the curve. And that's not so obvious when you look at this, but the shapes of the curves are also different. So as you go to higher spins, here the initial slope is steeper in the curve. So, and this is, again, these are the Brion curves. So here's one example for this. This is a compound, you were on there too, that we studied with Frank Meyer's group at Göttingen. So this is this kind of like large macrocyclic ligand, has 2 copper 2 centers in it, each one with a spin of a half. And they're ferromagnetically coupled, so the total spin is 1, but zero field splitting is very, very small in this compound, very small. Which means that the MS sublevels are essentially degenerate. And that, of course, is a requirement for Brion curves, right? The Brion curves are derived with the idea that all the MS sublevels are degenerate in the absence of the magnetic field. And that's kind of the case here. So then we can do this plot, right? So here are our Brion curves, now all normalized to 1, the intensity. And then we measure our saturation curve for this compound. This is this thing here in black. And you can see it lines up exactly with the S equals 1 curve. So the total spin of that system is 1. The centers are ferromagnetically coupled, and we can show it like this. But that doesn't always work, right? And it doesn't work when we have significant amount of zero field splitting. So it's always spin-orbit coupling. I'm always saying that ruins everything. It also ruins this, because once you have too much spin-orbit coupling, you lift the degeneracy of these MS sublevels. You get something like this, and then your curves are what we call nested. So the saturation curves taken at different temperatures do not overlay anymore. And now if you will plot this against the Brion curves, it's kind of all over the place. So you can't make that correlation anymore, unfortunately. So that correlation only works in certain specific cases. Okay, so let's go to the next step. This is a picture of Frank at ICBIC 1999. He's doing some karaoke there. But if you take a closer look, he's also thinking very hard. And you wonder, what is he thinking about? He's thinking about this, which is his famous general equation for MCD intensity, which is not limited now for the S equals 1/2 case, but for a general case. And so this has to be now expanded a little bit, right? Because now we have more than an MS plus minus 1/2 sublevel. We have a whole spectrum of them as our spin is larger. But essentially what you do is you do a spin Hamiltonian calculation where you figure out what the energies are of your MS sublevels, of your magnetic sublevels of the ground state. Right? And you have a sum here. The sum runs over all the magnetic sublevels. And of course, those are, if you're a little bit rhombic, you start to also mix up these MS functions. So In a general case, these are linear combinations with certain energies. Then you apply the magnetic field, and then you change them a little bit around again, and then ultimately you have to Boltzmann populate over all of them, right? And that's what's in essentially the sum here. So the sum is based on a spin Hamiltonian calculation that gives you the energy levels, then you Boltzmann populate over them. These are the Boltzmann population factors, then these NIs, for each one of these magnetic sublevels. And then we have three contributions here. So again, we have these effective transition dipole moments. So this is the same we had before, so nothing has really changed, right? So these triple products are still there. In order to make the equation more compact, then Frank wrote them in this M effective form, but you can see then it's the same thing we looked at before for the S equals 1/2 case. So we still have to have two orthogonal transition dipole moments and spin-orbit coupling in that third direction in space for MCD intensity to arise. And then what we also have in there now is a spin expectation value, and that's of course how this again connects to magnetism, right? So you have the sublevels, you have the energies, the population, and then you have spin expectation values for all of them. But you can see it's a conglomerate now, again. So our intensity that we measure certainly depends on this, but it also depends on spin-orbit coupling. It also depends on the transition dipole matrix elements, and so that's again why from the absolute intensity that we measure, we can't say what the total spin is compared to like a magnetic susceptibility measurement. So we can only normalize to maximum intensity of 1 and then look at the shapes of the curves and simulate those. And then we can also derive something else. So if we know the magnetic properties of the ground state, for example, we did some magnetic susceptibility, some EPR, some other stuff on our compounds, so we know what D values, E over D, G values are. We can put all this in, and then from the simulation, we can actually extract the polarizations of the electronic transitions, how they are polarized in our molecular framework. And that allows us then to really help assigning optical transitions. But well, not problematic, but the thing to remember here is that these polarizations that you get from your simulation are relative to the Zielfeld splitting coordinate system. So you got to know how your Zielfeld splitting tensor is oriented in your molecule, and then you can project the polarizations back onto the molecule, then you can assign transitions. So there's one step you have to take in between. So when I say the band is Z-polarized, right, then Z is relative to the Z direction of the Zielfeld splitting tensor, so you have to know what that orientation is. That, however, you can nowadays calculate with DFT, and DFT does always, not always, but oftentimes a pretty good job in doing this, so you have to do your typical, use a couple of functionals, compare the results, make sure it's all consistent, especially if you have one predominantly strongly bound ligand with a very covalent bond, and oftentimes the Z direction aligns with that particular bond, like in an iron 4 oxo or some iron nitrosyl compound, then oftentimes you see that that is the Z direction. Or in the case of a heme, where you have the XY direction is the plane, and then the Z direction is orthogonal to that. So this is something to keep in mind, but it's not an obstacle that you cannot overcome. Right? And then you can learn this. So now let's see, Carsten, do I have more time to do my examples, or are we out of time? How is it going? Oh, so otherwise we can also stop here. I started though 5 minutes late.
Okay, yeah, I think some of the examples, are you doing those in the practicals?
Well, in the practice we do different ones, but this is just some showing how we can use polarizations to assign transitions. I can maybe do the first one quickly. So this is an FeNO7 compound that we studied, so we're using here this TMG3 trend ligand, and then we made an iron 2 NO complex of this. This was done by Amy Spielman. And so this is Ennemark-Feldham notation, right? So the index 7 just means we have 7 valence electrons, so we have 6 d electrons of the iron and 1 pi star electron of the NO. That means valence electrons are 7, so we call it FeNO7. Here's the crystal structure of this complex just to show it's well characterized. Here's an EPR showing, so it has a typical S equals 3/2 ground state. This is what you observe for non-heme iron when you bind NO to the ferrous form, like in proteins also, then you observe this typical S equals 3/2 ground state. Okay, and electronic description. So it turns out that these complexes are actually best described as an IM3 NO- type complex. So we have a high spin IM3 center with a spin of 5/2, and we have a triplet NO-, and the spins are anti-ferromagnetically coupled, so up and down, gives you a total spin of 3/2. So that was first investigated here by Ed Solomon back in the 90s, who was the first to propose this. You can see this is why our electron counting scheme is good, right? So no matter if it's now iron 2 NO or iron 3 NO minus, no matter what, it's always an FeNO7. So it's a good way to keep track of the number of electrons that the system has. And nitric oxide, of course, is what we call a non-innocent ligand, so it is redox active, like this example here implies. So it gets reduced when it binds to the ion center. So we can also illustrate this electronic structure in this particular way. Then you might ask yourself, okay, how does this bonding work? And so we did some work on this, and essentially we were able to show that this NO minus ligand is mostly a pi donor to the ion free center. So you form these two very covalent pi donor bonds. They're essentially isotropic. And let's see, and you can see that these bonds are very covalent. These, of course, are the numbers that DFT tells you, so take this with a grain of salt. But what it tells you is, these are very covalent metal ligand bonds. And that's why these FeNO7 complexes are so stable, right, and not very reactive, because they have this very covalent ion NO bond. Anyways, we want to learn about optical spectroscopy now, of course. So this is just a little bit of the background. So here are now the data. If we take this FeNO7 complex, here is the absorption spectrum, here is the MCD spectrum that we get. Note here the change on scale, right? So this is a giant transition at about 368 nanometers, extinction coefficient almost 6,000. Corresponds to this curiously looking kind of A-term type signal, although it's a C-term, it's temperature dependent. And then these are much, much weaker transitions, right? So you ask yourself now, oh my God, what am I going to do with this now? I'm going to assign this. It's a big headache, right? So we can see if MCD can help. We can also ask former President Obama. He says you can see this here, right? It's got to be a rhombic, so all 5 d orbitals are split. So he got it right. That's a good starting point. It's indeed a rhombic complex, and so here, from here we can start working now. So here's the MCD spectrum again. It just shows you the field dependence. And now let's look at the saturation curves, right? Magnetic saturation curves. So if we look at the curves that we measure for these weaker transitions here in the visible range, you can see they're all strongly Z polarized, especially this big guy here. Is about 99% Z polarized. So the Z direction is along the ion NO vector. So this is a charge transfer now between the NO minus ligand and the ion free. These weaker transitions here are kind of mixed XYZ polarized, so those are probably DD transitions. But what about this guy here, right? Remember, this is the very intense transition about, if you take kind of the center point, around 368 nanometers by absorption, you can see that those magnetic saturation curves look completely different. They show this really, really large degree of nesting. And it turns out they're XY polarized. They're polarized in the XY plane, so these are charge transfer transitions from the guanidinium co-ligand to the ion free center. They're not related to the NO. Right? So those are, in a way, spectator charge transfer transitions that we observe here in this region. So we can assign now our bands very conveniently using MCD spectroscopy, and are looking at these polarizations. Again, in order to fit these curves, we have to put the magnetic properties already in to the system. We got to know what those are, like D value E over D. We got the D value for Mössbauer, and then we can do this. So this complex also exists in a 1-electron oxidized form, the FeNO6. This is a very interesting compound because when you oxidize, you get this huge absorption band that comes out about 550 nanometers. Right, and from the Mössbauer spectroscopy that Carsten here did in Bo, we're able to show that at least from an isomer shift, this oxidized complex looks like an iron 4. It has exactly the same isomer shift as Larry K's iron 4 oxo complex made with the same ligand, teams with Tren. And here's our FeNO7, here's an iron 2 compound. It's a nice correlation line. Here we are, right? Looks like an iron 4. So you might say, well, this is probably then a charge transfer now between this NO minus ligand and our new iron 4 center that we get from this oxidation. But again, who knows, right? So let's look at the MCD. And here's some more Mössbauer data. The Mössbauer data showed that this compound had this huge D value of plus 27 wave numbers from the Mössbauer simulation. And that gives us some really interesting properties for our MCD spectrum. Our MCD spectrum is really, really odd, because if you measure this as 2 Kelvin, you have like almost no intensity. And then as you warm it up, the intensity rises. It's completely opposite to Stevens' equation, right? It goes the opposite way. The 1 over T is not followed at all. But the way you can explain this is with this large zero field splitting. When you are sitting at 2 Kelvin, right, all your molecules are in this non-magnetic zero state. And it's an axial system. So there isn't too much mixing here of the MS sublevels. And then you need to warm up to populate the magnetic +-1 level in order for MCD intensity to arise. And so here the intensity goes up as you warm up the sample. It's a really crazy spectrum. We were sitting over this and looking at this for a while. Then you notice that, oh, look at this. This looks like a pseudo-A. So maybe this is actually now my guanidinium to iron 4 charge transfer. That's all up there now at 500 nanometers. And indeed then, look at these magnetic saturation curves. They're like totally crazy, but it turns out you can simulate them with a D value of about 33. So Mössbauer says 27, MCD says 33, so let's get together in the middle, say D is about 30. You can simulate those curves. And they're exactly XY polarized in the plane. Oh, so this is actually the guanidinium to iron charge transfer that moves from 368 nanometers to about 515 in agreement with the idea that we oxidize the iron center from iron 3 to iron 4, which lowers the d orbitals in energy and should shift the charge transfer more into the visible range. So I'm already over my time, so I think we're just going to skip the summary here, because essentially this is the stuff that I just told you about. And so if you sign up for the MCD module, first of all, please install this Origin trial version, because that's the program that we're going to use. And then you might encounter one of these three guys here, Hai, Jill, or Corey, which are my students who are going to teach the MCD tutorial. And with this, I'd like to thank you for your attention.